Hello everyone, this is Karen Nafi. I'm currently a second year master's student in the Department of Geography at the University of Kentucky. So the work that I'm presenting today is an extension of my master's thesis work. So the work is entitled Characterizing Multi-Year Species Level Phenological Variations in Urban Trees using PlanetScope Imagery. My co-author is Dr. Liang, who is also my thesis advisor. So firstly, we have to understand what plant phenology is. So basically, vegetation phenology or plant phenology is the study of various events in plants' life cycle. And typical vegetation phenology events include bud emergence, leaf development, senescence, etc. And these are ecologically important because these phenophases are biological events represents how species react or responds to climate change. So after going through various literatures of previous works that have been done, particularly in this area of research, we have found out that the conventional remote sensing satellite images that are being used in vegetation phenological studies are typically coarse, spatial, and spectral resolution based. So this makes it difficult to analyze the tree phenology at species level. And the second gap that we have found is the avenue of using thermally normalized phenometrics to classify individual species is insufficiently explored. So phenometrics is basically the phenophases or phenological events that occurs in a plant's life cycle. So based on these two research gaps, we have tried to position our research in addressing two particular objectives. So the first one is to characterize species level phenological profiles of urban tree species using thermally normalized AGDD, which is accumulated growing degree days phenometrics derived from PlanetScope imagery. And the second one is to assess whether data or features derived from PlanetScope imagery can act as an effective indicator for species identification. Particularly, we will do a comparison between one machine learning algorithm, which is random forest, and one deep learning algorithm, which is MLP or multi-layer perception. So we have mainly three data sources. One is PlanetScope imagery. So we collected images for dates from 2023, 2024, and 2025. So typically we use a cloud filtering to filter out the images which has more than 10% of cloud cover and only retain the images that has less than 10% of cloud cover and use them in our research. The second data that we used is the UK tree inventory, which is compiled and maintained by the Arboriculture Department of University of Kentucky's Grounds and Facilities Management. So this is a CSV file which contains the tree IDs, species name, DBH, which is diameter at breast height, and precise coordinate location of each individual trees, that is latitude and longitude. And the third dataset that we used as a source is the NAIP aerial imagery, which is a 0.6 meter spatial resolution aerial image. So particularly we use this aerial image as a reference to correct our tree locations and the canopies that we generated from that tree inventory data. So the inventory tree data had more than 12,000 different trees, but we filtered those out and only used the natives and most commonly occurring species in our study area, which is the UK main campus, and we found 18 different species. Um, Under these 18 different tree species, we have around 2,678 individual trees. So we used that tree inventory data and converted it to data points. Later on, we applied a scale factor to estimate approximate canopy extent for each tree, and the scale factor we used were derived from the work of Hemery and Bethold, and each different species has each different scale factor multiplied to its dBH, which is diameter at breast height, and then we applied a unit conversion, and that is how we determined the approximate canopy extent. And using that canopy extent data, we converted this into buffer rings in order to cover the maximum extent of tree canopies, having the tree point at the center. So after that, we did a need-based manual adjusting of individual tree polygon or canopy polygons in campus using the NAIP imagery as a reference, typically to fix the tree locations and the canopy extent which were not in the right place. So we computed four different vegetation indexes, two from broadband indexes, which are normalized difference vegetation index NDVI and enhanced vegetation index EVI2, and two red edge vegetation indices, which are normalized difference red edge index index and the chlorophyll index red edge. So time series of these vegetation indexes were derived from the PlanetScope imagery data. So basically time series of vegetation index data are regarded as one of the main data source that is used to infer vegetation phenological parameters. We also derive vegetation seasonality indicators following the framework of Dr. Jeffrey Hennebree. So VSI, or vegetation seasonality indicators, use dense time series to form non-parametric statistics to compose seasonal slides, including maxima, median, and the difference between them. So for each year and for each in the indices, 10 seasonality indicators were computed, and here you can see a list of 10 different seasonality indicators that we computed from our data. So from the time series vegetation index data, we derive phenometrics. Firstly, we applied the Savage-Nicolai smoothing and then spline interpolation to create a clean seasonal curves for each tree. And later on, phenophase dates were extracted using the percentage threshold of segment amplitude. So we typically extracted 6 different phenophases. The first one is green up onset, which means that when a date of vegetation index data crosses 15% of the rise, we termed it as green up onset. When it crossed 50%, we termed it as mid green up. Then at 90%, we termed it as maturity. And then when it started declining, so 90%, when it starts declining from the peak, we termed it as senescence onset. Then 50% at mid senescence and 15% at dormancy. So we typically follow the framework laid down by Gray, Salamenash, and Friedel, and extracted these phenophases for our work. So we used AGDD, which is accumulated growing degree days, which is a form of thermal normalization of phenological timing, instead of using the day of the Y or DOY, which is typically used in vegetation phenological studies. So the purpose of using AGDD instead of DOY was to make sure that we get a metric that is biologically consistent across years and across tree locations. For extracting AGDD, we use Lexington Bluegrass Airport Station data. So daily temperature records from 2023 to 2025 were used. And then we converted the DOI into accumulated growing degree days using the formula of estimating AGDD from DOI. So lastly, after extracting these different feature data from our time series data, we applied one machine learning algorithm, random forest, which is an ensemble tree method, and one multi-layer perception algorithm, which is a deep learning algorithm, in order to compare which algorithm works best for this type of tabular data. And we also use different combinations of our featured data. So we used 7 different combinations in order to find out which particular combination has the most significant discriminatory power for species identification, and we evaluated and compared this across 4 different vegetation indices. So now moving on to the results section of our study. So firstly, as you can see here, we have 4 figures that shows phenological calendars, one per spectral index, and this was generated using the mean of the annual median AGDD across 2023 to 2025. So looking at the dark green bars in the figure, this represents green up to maturity phase, and all 18 species, as you can see, initiate green up within a compressed thermal window, and among them American sweet gum brings up earlier at around 700 AGDD, and this species is broadly consistent across all arms for vegetation indices. The orange part shows much greater spread, which represents senescence to dormancy, and as we can see, shade master honey locust has the most spread across the all 4 vegetation indices, and this early and distinctive senescence phase kind of represents a clear phenological fine print in our data. So after that, we did a statistical analysis and applied the Kruskal-Wallis test to see whether the phenophases are significantly different in each species. So since we were dealing with a large number of data, so there were obviously significant differences in phenophase timings. But in order to derive something meaningful from the data, we did epsilon square, which tells us what proportion of variance in phenological timing is attributed to species identity. So for NDVI, we see mid senescence has the highest epsilon squared value, and for EVI2 also mid senescence. But for broadband red edge based indices, NDRE mid green up, and similarly for CIRE mid green up has the highest epsilon square value. So the interannual rank consistency table shows Spearman correlations for 2023 to 2025. Mid green up and mid senescence are consistently green across four indices. High rank stability, meaning the species ordering is preserved from year to year. So the exception here is in terms of maturity, particularly for NDVI and EVI2, which shows near zero correlations. So which means that broadband indices saturate at peak canopy and cannot reliably distinguish species at maximum greenness. However, for red edge based indices, NDRE and CIRE, we can see they have values 0.68 to 0.80 even at maturity stage, which means that these indices have a clear advantage over the broadband indices. So onto the classification results. So across four indices and seven feature combinations, random forest consistently perform best when combining HEDD phenometrics data with the spline derived vegetation index data. So among the four different indices, NDRE achieved the highest balanced accuracy at 76.5%, having the phenometrics plus the NDRE spline as the best combination. Red edge indices marginally outperform the broadband indices, which typically is consistent with our findings before that red edge bands maintains high interannual rank consistency. Seasonality indicators, however, were less important in terms of having distinctive species identity, and thus they perform poorly in the random forest model. Importantly, according to the feature importance, we found that mid senescence and mid green up, the exact two phenophases with the highest epsilon squared values, had the most feature importance in classification. So these two completely independent analyses, one from non-parametric statistics and one from machine learning, converge to the same biological signals. So basically, this method kind of gives us strong confidence that PlanetScope is genuinely effective in extracting species specific or species distinctive phenological data, particularly at mid greenup and mid senescence. Now onto the comparison between random forest and MLP, we see that random forest consistently outperform MLP by approximately 25 percentage points, particularly at balanced accuracy metric. It also outperforms MLP in overall accuracy and F1 values as well. So this kind of reflects that there is a clear advantage of ensemble tree algorithms, particularly for tabular data over the deep learning algorithm. So the NDRE derived feature through random forest algorithm delivers the best classification accuracy. So we use that in order to find individual species accuracy in our data, and we found cherry bark oak, willow oak, butternut hickory, honey locust, white oak, and white ash deliver accuracy between 60 to 80%, as well as F1 score in that zone. And the lowest and the least accuracy we got from pignut hickory, eastern dogwood, American beech, pine oak, and red maple. So to conclude, we can say 8-band PlanetScope imagery reveals statistically significant interannually consistent species level phenological differences across the three species in our study. Mid senescence and mid green up is the most discriminatory and temporally stable phenophase across four vegetation indices. NDRE random forest achieved the highest balanced accuracy. Random forest consistently outperform the deep learning multi-layer perception, and the phenophase identified as the most statistically discriminatory by Kruskal-Wallis analysis are the same feature most predictive in the random forest classifier, providing cross validation of PlanetScope species level discriminatory capacity. So with that, I conclude my presentation. Thank you so much.